This is resistance. This is John, Shane, and Cooper.
What is resistance? The official definition for resistance is the amount of voltage required to make 1 amp flow through a circuit. For example, if it takes 500 volts to make 1 amp flow, the resistance is 500 ohms. From this, we derive Ohm's law, which tells us that V equals I times R, where V is the voltage difference between 2 points, I is the current, and R is the resistance.
So how resistors work is basically due to the molecular configuration of the resistor, and this configuration can inhibit the flow of charges by altering the way that the electrons pass through the material. So longer chain molecules like plastics are going to inhibit the flow, while the flow of charge and current, while crystalline structures like metals allow electrons to move much more freely and have less resistance per unit of area. So different resistors made of different materials with different molecular configurations are going to inhibit the charges to different degrees based on those different configurations. And you can see here in the figure different types of resistors with different materials used in them.
Does size matter? An easy way to visualize resistors is to visualize water running through a pipe. Imagine you're trying to push water through a pipe. Different pipes will allow you to push different amounts of water through. A girthier pipe will resist the water less than a narrow pipe. Similarly, a shorter pipe will have less resistance than a longer one. Imagine filling a pipe with sponge, sand, or pebbles. You have now limited the flow of water through the pipe, much like a resistor resists the flow of electrons through a circuit. Electrical resistors are similar. The longer or thinner a wire is, the harder it's going to be for electrons to pass through it. Likewise, if you change the material the wire is made from, a conductor to an insulator, you're also going to affect the flow. The relationship between resistance and size and type of material from which a resistor is made is given by this equation. And as you can see, the picture offers us a variety of resistors.
All right, so I'm going to talk about the range of the resistance. This kind of goes off of how resistors work, which Cooper talked about. So materials have very different resistivity that affect the point at which the current easily flows. The difference from metals to non-metals in terms of resistivity is in orders of magnitude. So silver, which is the most conductive, which is the least resistive element, has a resistivity of 1.6 times 10 to the negative 8 ohms, while hard rubber has a resistivity of 10 times 10 to the 13 ohms. So this is an order of magnitude of nearly 21. This is why wires easily allow electricity to flow through them, and the wire resistivity is so much lower surrounding the rubber. Yeah, and it's not easy for the electricity to pass through the rubber.
So in circuits, resistors are used to modify the amount of current passing through the circuit for a given voltage, and it also leads to the dissipation of power, which is also we see as the production of heat. Resistors can be used to make separate voltages and divide the amounts of current passing through different paths of the circuit. As you can see, the voltage across a resistor and the given current traveling through that path, the power dissipated is equal to the voltage times the current, or the current squared times the amount of resistance. So by increasing the resistance, the amount of power dissipated also in turn increases. Which leads to an increase in the amount of heat produced.
Resistance and temperature. Resistance of a material isn't constant. It steadily increases as the temperature increases. This is because when a material heats up, its atoms vibrate more and it's harder for electrons to pass through the material. This restricts the flow and increases resistance. The same can be said about cooling a material. If you lower the temperature of a material, you can actually lower its resistivity. At extremely low temperatures, it is possible to make resistivity disappear altogether. This is known as a superconductor.
Superconductors are materials capable of carrying current with zero resistance or any dissipation of power at extremely low temperatures. Their technology can lead to more efficient power distribution and transport from power plants, as well as the production of powerful magnetic fields used in MRI and Higgs boson detection. To make the most of dissipated power, as current passes through a resistor, electrical energy is converted into heat and the power is dissipated. The heat produced by the current passing through the resistor can be used as a source of thermal energy, like in the coils of a toaster, stovetop, or hairdryer.
As power dissipation, as current flows through a resistor, like the filament of a light bulb, heat is generated and the atoms are excited to a higher state, then returning to a normal energy state and emitting light. we see it. And we know from lab that light bulb filaments are non-ohmic material, unlike a resistor, which is an ohmic material.
Resistors also have applications in a wide variety of things, such as sensors. Resistors can be used in sensors such as gas sensors and lie detectors, but are not limited to. Fuses are resistors as well. Fuses must have a small resistance in them to dissipate enough heat to burn themselves up when their current rate is exceeded. Fuses are used in circuits to ensure that a circuit is not damaged by an excess of current. So what a fuse does is, if an excess of current is passing through the circuit, it's actually going to heat up the fuse and make it burn up so that it shorts the circuit. That way you end up having to replace a fuse and not replace all the components of the circuit.
Control damage.
Yeah, control damage in the circuit.